All right, in this demo, we're gonna talk about power and energy. So here's a capacitor here in blue. What I'm gonna do is hook this capacitor up to a battery, charge it up, and then I'm gonna cut the switch to the battery. This will stay charged, and then I will flip the switch so that the capacitor is then connected to a light bulb. So the charge will then go through. The charge on the negative side of the capacitor will migrate through the bulb, light the bulb, back to the positive side until all of the charge on the capacitor has flown through the bulb and caused it to light for a certain amount of time. So my question is, which bulb, if we use the same capacitor and connect it to the same voltage and charge it up to the same Q on our capacitor, which bulb will last the longest? I have here a 150 watt bulb, and I have here a 15 watt bulb. So why don't you take a second, pause the video, think about the answer to the question. Which bulb will stay lit the longest if we charge the capacitor to the same amount and use that charge to flow through the bulb? Will the 150 watt bulb stay lit the longest, or will the 15 watt bulb? Okay, now let's do it up. So on my meter here, the meter on the left will show me the current as a function of time. So right now what I'm going to do is connect the capacitor to the battery itself to start the charging process. You'll see the current jump up and then slowly go down, because right when we first connect the capacitor to the battery, charge will flow very quickly, but as we build up charge on the negative side of the capacitor, it'll be harder and harder and harder to force more electrons onto that negative side. And so the current will go down exponentially as a function of time. We'll learn about why that is next week. But so if you watch this meter, you'll see the current go high and then slowly go back down. So I'm gonna watch it until it goes down by about 95% of the way so that the capacitor is fully charged. Okay. So let's charge up. And as you can see, the meter is showing us that the current's going down, 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 down. And so we probably got about 95% of the charge on there now. So what we're going to do is when I flip the switch now, I'm going to connect the capacitor just to the light bulb itself. Charge is going to flow through the light bulb, light it up. We're going to count and see how many seconds it stays lit for. So this is the 15 watt bulb. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 10 seconds for our 15 watt bulb. Okay? So let's do the same. Replace that 15 watt with a 150 watt bulb. And we'll see if your answer was right. Which is going to stay lit the longest, the 150 or the 15 watt? Okay, so we're fully discharged now. So we're going to charge it back up. Again, you can see the current was high at first. We'll slowly go down as that charge, more and more charge is building up on that capacitor. I'm going to wait till it gets about 95% lower. Okay, that's pretty much fully charged. So get ready to count, see how long this one stays lit. Ready? 1/1002. Not even 2 seconds. So big difference. So let's explain why that happens. So if you didn't get the right answer, now you can understand why. So which bulb stays lit the longest? Well, the wattage of the bulb tells us the power it's using. 15 watts will use 15 watts of power. And 150 watt bulb will use that. Power is always the energy used, the change in energy per delta T. In this case, the energy is the same in both cases. U is 1/2 CV squared for our capacitor. We didn't change the capacitor. We didn't change the voltage we hooked it up to. We let it fully charge. So that mu was a constant. So this was U, our capacitor's energy, divided by delta T, the time over which it stayed lit. So this means P is proportional to 1 over delta T, the time it stays lit. So the larger the power, the lower the time it will stay lit, because delta T is in the denominator there. So the 15-watt bulb will stay lit for the longest, 150-watt bulb shorter. Okay.